So my name is Edward. I work at Yahoo Research, and I'll be actually representing the real people behind this project, which are Ashkar Hillel and Anastasia Bruginsky. And we'll have a chance to explain where its name comes from at some point down the road. These are the main contributors. There are also new HBase committers, by the way. And I just want to use this chance to thank our partners who were terrific: Michael Stack, Anup Sam John, and Ramkrishna Vasudevan from Intel Bangalore. We unfortunately we do not have Ramkrishna's picture today. So in this project, we are actually in the quest to achieve the user's holy grail, which is on the one hand to maintain the hard guarantees of reliable, persistent storage that that HBase provides, and on the other hand, try to approach the in-memory database performance. So here's the idea. So what is actually Accordion? It is a new algorithm that deals with the write path in HBase. It's not specific to HBase. We can actually apply it to any modern key value store design. It improves the performance of write intensive workloads, increases the write throughput, and if you read in parallel to writes, it also drives the read latency down. One more important feature is that it uses the disk much better. In the other words, it drives write amplification low, and it's going to become generally available in HBase 2.0, where it actually will become the default MemStore implementation. So the idea in a nutshell is inspired by the log structured merge tree design that is prevalent in most of the modern key value stores. So just in a nutshell, log sequence merge trees transform the random I/O to sequential I/O. This design governs the HBase storage organization, and the main idea behind LSN trees that were born sometime in the early 90s is to avoid constant rearrangement on data on disk that plagued the previous best-in-class B-tree designs. And actually, the LSN trees emerged when memory was very expensive and scarce. And right now, it's not the situation. We've got plenty of memory on our machines. So we just thought, could we reapply the LSN tree design to memory resident data? And the idea is, can we have it this way that data would live in memory longer, that we could perform less I/O and ultimately achieve higher speed? So before we actually get to the Accordion ideas, this is how LSM trees work in a nutshell. So we have two separate paths: the read path and the write path. The write path, the put operations are absorbed by the in-memory buffer that is called MemStore, and every once in a while that buffer overflows and is being flushed to disk, where creatures called H files are created. So there are bigger H files and smaller H files that are actually accessed by get or scan operations. So every get or scan, when it needs to pick some key or bunch of keys from from HBase, it has to access both the MemStore or the H files via the bucket cache. So the entire thing is stored as a sequence of versions. So the same key, the updates to the same keys may be stored both in MemStore and in the H files, and we figure out which is the right version in the read time. So every once in a while, a process that is called compaction kicks in, because we want to keep the number of H files low, basically to reduce the read latency. So this process rearranges the H files. It merges them into larger files. So if we look at LSN trees in action, we see that the same MemStore is each time the MemStore overflows, it flushes stuff to the disk, and once we have too many H files on the disk, a compaction kicks in. So it happens once in a while, and it's pretty painful process. So we'd like to have this event as infrequent as possible. So basically, when we speak about Accordion, it's exactly the same thing. It just reapplies the design, the LSN tree design to the in-memory data structure. So what we thought is, what if instead of managing a single big monolithic MemStore, can we actually slice it into a bunch of segments, out of which only the most recent segment is active and is being actively updated, and the others are immutable. So the process is pretty much the same as with the basic LSN tree design. It's just that the immutable segments are memory resident and not backed by files. So this whole new creature is called Compacting MemStore. Why is it called Compacting MemStore? Because every once in a while we can run compaction in among the immutable segments, eliminate the redundancies, and create a more efficient index representation than we used to have with a single big monolithic active segment. So in action, Accordion looks pretty much the same as the basic LSN tree design. We just have a new layer, a new creature in the middle. It's called compaction pipeline. And this compaction pipeline is basically a container that holds the immutable segments that we can maintain and merge sometimes before flushing them to disk. This process basically happens in parallel with the other processes that go on in the region server. For example, the higher level process can decide that upon flushing this region stuff to disk, this is fine. At this point, all the data in the immutable segments is moved to the snapshot that is used by the disk flusher thread, and so on. So these processes of in-memory compaction and all-disk and on-disk flush are largely independent. They need to synchronize from time to time, of course, but we can manage the pipeline in a pretty independent way. So getting down to the data structure level, the MemStore internal layout used to look like something from the left side of diagram, it uses a concurrent skip list. It's a huge concurrent skip list that is actually linked to the cell storage data through small objects called KV objects that actually contain references to the real cells. As you see, it's full of references by itself. So it's the more cells there are, the more internal nodes in this skip list we have, the more overhead we invest in storing references. So the most basic optimization is just rearranging this this index in the read-only immutable segments in the way that that we don't have this this overhead. So basically, just storing a sorted array of of references to particular cells. So the basic partition between the skip list the storage and the cell array map storage is like 25% to 75%. So we really save a lot of references this way, and of course the smaller the cells, the leaner the layout. So how do we eliminate redundancies? So the in-memory compaction process is something that that kicks in once in a while, and it can merge the pipeline pipeline segments, just as in the case with compacting the on-disk H files. We do need to merge the pipeline segments every once in a while if we want to keep the read latencies low. So it comes actually in two flavors. The basic compaction merges only the index data. So going back to the previous slide, so it only takes these red chunks, red indexes that belong to multiple segments and merges them. Whereas the eager compaction is something that actually eliminates the redundancies in data. So assuming you have like heavy tail distribution, depending on how much skewed there are, we can reap a lot of performance from eliminating the redundant versions as well. However, this process is much more costly because it is about relocating much more data than basic compaction does. So for that reason, we do not recommend eager as default optimization. It can be enabled, but you really should know what you are doing. Basic is doing pretty universal things, so it brings no harm, which we have shown through very extensive benchmarks. So, however, we're still working on a smarter version on this code, in which the system will figure out kind of automatically the nature of the workload, so that the administrator will not have to worry about this specific configuration. So a couple of words about the implementation. So the compaction pipeline is actually a data structure that is shared among many components of this the system. So the gets, the scans, and the in-memory compactions, both all of them actually read from it, and it is also access for writes by in-memory flash, in-memory compaction, and disk flash, because they replace stuff in this shared data structure. So based on the benchmarks, we made the design choice that the reads should be non-blocking, which means that most of the reads access a read-only clone of this pipeline that stores references to the existing chunks, to the existing segments, and it uses a copy and write modification. So each time, for example, the in-memory compaction kicks in, it creates a single merged segment aside, and it atomically switches it with the existing pipeline clone. If something happened to the pipeline in the meantime, like the in-memory flush happened and a new segment has appeared, then we can always cancel the result of in-memory compaction, since it's just an optimization, and run it anew. So this this almost never happens. So this way we avoid a lot of synchronization in accessing the in-memory pipeline. Okay. So right now there's one more thing I want to tell you about before we jump to the performance results, which is further optimization of this data structure, in which we eliminate the cell objects. Okay, so see all these blue cell objects. They are actually convenient because the cell array map is easy to organize. It uses regular Java references, but on the other hand, they create a lot of fragmentation and eat up a lot of memory. So the next optimization actually folds them all into the single flat index that is called cell chunk map. And the interesting thing about it is that it ceases actually using using references. It uses the unique unique cell IDs for addressing data within the cell storage within the chunks, and even the index itself can be offloaded to the. It's very friendly to off-heap implementation, because the whole index can be actually put off-heap. So there is a very nice project that is running in parallel, which takes care of off-heaping the read path. So this project is complementary, because it can put actually the whole write path off-heap. So a couple of words about, about the software side. What's new? We have implemented a new kind of new type of MemStore, which is called Compacting MemStore. We still keep the default MemStore around, but it's not the default anymore. Like so there is a flag that controls the implementation, and we can by saying that you don't need any in-memory compaction, you can basically switch the default MemStore on, but we don't recommend doing that. So there is a whole bunch of new first-class citizen, like the segment class hierarchy. There are mutable segments, immutable segments, composite segments. These segments actually deal with new index types, which are implemented as navigable maps, cell array map and cell chunk map, and the whole compaction algorithm sits in a class that is called MemStore Compactor. Unfortunately, we don't have time to go into that, but we have recently posted a couple of blogs and blog posts, and whoever is interested can look that up. So there are some challenges in managing the cell chunk maps, the flat indexes. As I just said, we reference the cells not through regular Java references, but by chunk IDs, and for that we had to redesign the whole process of chunk creation, so that we can track those references and make sure that we don't get in the way of the normal garbage collection. So there are some quite exotic use cases of which we have to take care of. For example, there are some applications that use jumbo cells that don't fit into a single chunk. So for that, we need custom implementations of chunk allocations, in which custom sized chunks are allocated for just those cells. Okay, so let me say a couple of words about the evaluations and of this new algorithm, and how we actually concluded that it does good things. So we experimented with that on a small HBase cluster, but under pretty heavy workloads. So the machine configurations, hardware configurations, and HBase configurations are similar to what we use in production, and we use the workload YCSB as workload driver. So what did we measure? We measured a bunch of metrics here. We measured write throughput, the read latency, when read and write latencies. When we speak about latencies, it's basically about the distribution. We look at different quantiles, and we also look at the disk footprint that the new algorithm has compared to the previous one. So we looked at a bunch of workloads which we vary at the YCSB side. Write-only workloads versus mixed read and write workloads. We looked at different key distributions, uniform versus heavy-tailed, and also played with different value sizes. So the configurations at the server side, we actually played with both async wall and sync wall configurations, and we ended up. I'll show you the figures only for async wall, because the sync wall is just so slow that for every single write you dump a record into the log that it actually kills all the optimization that comes from this method. So in most production settings that we are aware of, most of them take this trade-off of using the async wall. So let's start with the write throughput. So so as you see in the zip write throughut, the heavy-tailed write throughput, we get something like 25% improvement versus the custom implementation, and a slightly the default implementation, excuse me, and a slightly less improvement if we use the eager algorithm. And the reason for that is that the eager algorithm actually spends many cycles on compacting the data in memory. So this is the reason that during those cycles it doesn't use the CPU cores for actual work. So its write throughput that it achieves is a bit lower, and this is even more pronounced, much more pronounced for a uniform for the uniform workload. So for uniform workloads, as you think of it, there is no actually reason to try to compact the data itself, because there are no redundancies in the data. So there is no reason to move it around from one buffer to another, and because there is no actual gain for that. And I should also say that these gains are most pronounced for small cells. When cells become bigger, we see smaller gains. So for write latency, we also see some modest gains, but which are actually much smaller than for the write throughput. But this is easily explainable because the whole process actually happens in the background, so it does not affect the write operations themselves as they happen. It just optimizes the footprint of the data in RAM, but the writes are still a little bit faster because they operate on a smaller data structure. Actually, the active segment is 25% of what it used to be in the previous default configuration. So that's why it's less time to access a data item in it. So for that reason, the write latency is a bit faster. So nice thing here is to look at the read latency, and as we see, the basic algorithm, which is in blue, actually gives a little bit of increase of read latency under the zip configuration. And anybody has an idea why? That's because we actually, when we have a number of segments in the pipeline, so we have to look in more locations. That's why a small increase in time. So it entails no I/O, but still more time when we have. Normally we have just one segment in the pipeline, but since the in-memory compaction is an asynchronous process, then sometimes there are more than one segment in the pipeline. And as you see, the eager algorithm brings quite a bit of savings in the read in the tail read latency, because at the end of the day, the data lives more in memory. We write to the disk less often. We need less compactions, and there is less movement of data between the memory and the disk, and it all manifests in these numbers. So just to underscore what we just said about the performance, here is how it manifests in the disk activity that measured in the system. So again, we are speaking about the heavy tail distribution, and in this context, we have a lot less flushes, a lot less compactions going on, and at the end of the day, there is a lot less data written to the disk. So we have also a nice bonus of a disk of a smaller disk wear out. So let me finish here. Well, we have so there is one slide that doesn't appear here that speaks about the GC impact of the new algorithm. So we do see a small reduction in the GC pauses. We see like 20% of reductions in the GC pause time. And cutting straight to the status. So this project is GA in HBase 2.0. There is an umbrella Jira with about 20 subtasks. We've published some details about that, many details actually, in the Apache blog posts, and some of the work is still in progress with the cell chunk map part. So at the end of the day, Accordion is a leaner and faster write path. So I did mention why this project is actually called Accordion. This is because the memory footprint looks like accordion bellows. It grows and shrinks over time. Okay, so this is the reason. It's a space efficient index. We do less I/O. We flush less. we compact less on disk, the data stays longer in RAM, so the whole system kind of breathes easier with this whole thing. And let me just conclude by thanking our partners once again. You were awesome, and for letting this project happen.